This is a video in a series in which my goal is to build a poker bot, and I left off with the last video about 3 months ago, and I kind of burned out, to be honest. I stopped working on it like 2 months ago, but in that last month after the last video I actually made some pretty cool things that I wanted to go over, and I hope making this video will motivate me to continue working on this. And so basically what I did in the last video is I was still just playing with toy solvers, but I realized after the last video that if I was going to make any progress on this at all, I was going to have to just jump in and make a full solver, because at the end of the day these AI algorithms all basically assume that you have the full solver, because it's essentially the same thing as a normal counterfactual regret minimization algorithm, except there's extra functionality on top of it. So like instead of using a leaf node, you can just stop at a certain depth limit and then return one of the values that comes from the abstracted tree. So you need to be able to toggle that on, and then you also have to do additional stuff after the fact to like basically dynamically build a tree. So you give the opponent different options to choose from as you're solving the thing. And so it's actually a more complicated version of counterfactual regret minimization. And also, in order to even solve the abstracted game, that's also extra functionality on top of normal CFR, because you have to be able to map the actual game to the abstracted game and save those values somehow. And so I thought definitely what I had to do was build a full poker solver. So the way that I went about making this thing is I basically took this project by this user named Fasana called Discounted CFR Poker Solver, and I actually mentioned this in one of the previous videos. And this is just it's basically it's a CFR solution for the full poker game. So it's not a toy game, but it's not quite the same as some of the algorithms I went over in the previous videos. He actually uses vanilla CFR, so it walks the entire tree. It doesn't do any sampling. And so I am going to have to make some changes to it, but for the most part this works as far as I can tell. Although it only solves from the flop onward, so I'm also going to have to make some changes there. But for the most part it works. It's just incredibly slow now because it's written in Python, but my plan is to convert it to Python, hopefully. And then that would be able to speed it up so it would run in a reasonable time. And the reason I wanted it to be in Python is just because I just think it's going to be easier to work with, and then maybe in the end when I actually have it working, if I could then rewrite it in C++ or whatever, so that to get the the maximum performance out of the thing. And so yeah, so I wrote that, and I made the front end, because this project, it doesn't really have any way of looking at the output of the data that you solve. Basically it just in the console it like outputs the final exploitability or something like that. And so I made this full little front end for this thing. And so I think I'll explain this layout in case you're not familiar with this type of thing. I actually got the idea from, it was actually one of the first commercial solvers. It was used by, there was this poker player named Canoe. I think his name's actually Alex Miller. And he used to play back from like 2010 to like 2020 or whatever, 2020. And yeah, in one of the first solvers they used this type of layout. And the idea is, instead of like normal layouts with the in a solver like Pios, they put the suited hands in the top right and the offsuit hands in the lower left. And here instead what we do is the entire range is represented in like this upper corner right here, and each cell is an individual combination. So this is like ace 10 of spades, and let's say this is like queens with club and a heart. And so you can actually see the suits. I made this little button so you could see. So each cell is like the individual suits. So you can look here, like this is a 7 and this is a king. So right here is going to be king 7 of diamonds. And it's actually not in the range, so we can't see it, but that's the way this thing works. And then one of the benefits of having it like this is, once you get used to it, you can see that like this is we only have king jack suited in our range because we only have these 4 combos going down the diagonal. And so you can see basically if you have if you have both like ace king and ace king suited in your range, and if the suited cards played differently, you would see that just because going down the diagonal would look differently. It would be different colors, and so the color scheme I'm using here, it's actually grouping them by the strategy. So like the things that have the same color all have a similar strategy. So here, like the blue means that you're mostly checking or almost 100% checking. Let's see, this one red is like 65% check, so you can go through here and see that it's around that. And eventually one day when I actually write the full abstraction, I'd like to have it so that I could do the so you would have the abstraction directly within this this solver, because really I'm making this so I can basically investigate the outputs of the bot and the abstracted game. I'm not really going to use this to study the game of poker, but I do like this type of layout just because it seems like there's all the data's right in front of you. You don't have to like hover over things to you know, see if what combos are actually doing. And one of the benefits of having all the cards or having a full range in the upper right corner is you can then isolate individual combos in the lower left corner. So that's what I did here. So if you want to see what checks, you just toggle this thing up here, and then that shows you the part of your range that checks, and this will show what bets, and you can toggle multiple of them when there's multiple actions. I'm not sure where there are. Not here. This is kind of like a junky solution that I made because I was just debugging stuff. And so that's the way this thing works, and for the most part I think it works like any other solver. You can kind of navigate up and down the game tree with these buttons up here, and when you hover over the different combos, it kind of gives you some information about the strategy that you take there. So here with like king queen of clubs, we fold 54%, we call 45%, raise 0%. Pretty standard stuff, except I'm really doing this to investigate the expected value, or like the value of the node, because that's really what I'm interested in when I want to compare the abstracted game that I'm going to solve to the full game. So the idea that I had is that I can basically solve a hand from the turn onward using the full solver, and then do the same thing with the abstracted game, and then I can open it up in here and just look and make sure that the abstracted game solution actually makes sense, and that it's for the most part mapping to the you know, it has roughly the same strategy and roughly the same EV for the, you know, the different buckets, because I think it would be kind of strange if they were really far off. So that could help me figure out if anything's going wrong. And the other thing I have implemented is I actually made a visualization for the full game tree. And so, because this was actually kind of more difficult than expected with the actual implementation in Fasana, is like the part of the code that builds up the game tree, like takes into account like whether you can make an all-in bet based on whether it fits the, you know, your all-in threshold or whatever, and handling that type of thing. That type of code is actually a lot harder to write than I expected. And Fasana, he actually made some like small mistakes, not really in terms of like programming mistakes, but like in poker terms he made some mistakes. Like the way that he calculates like a 50% raise is he takes the size of the pot and their bet, and then just takes 50% of that, and that is not correct. You're supposed to make it so that it's the size of the pot, their bet, and then as if you called, then you put 50% on top of that. That's how you calculate a 50% raise, because otherwise you're going to give the opponent different calling odds for like a 50% raise, where it depends upon the size of their bet, and that's just not the way it's supposed to work. So there's lots of small things like that that were not implemented correctly. And it also shows you just like how big these game trees can get, because like, you know, when you see that it's all 52 cards and each one kind of branches out, yeah, the game tree gets pretty big. I purposely made this one small to like not have that many actions on the river. But yeah, so I have this for basically investigating whether whether the actual game logic is correct, because it's one thing to have the CFR logic correct, but if you mess up like the actual bet sizes and like how much money's in the pot, like the whole thing's just gonna collapse. And one more thing I wanted to add was that that this tree that I have here, the full game tree, this corresponds to basically the data structure that the actual implementation is like, because unlike in all the toy game solutions that I did, where you basically have one information set being one node, so that's like one individual hand, in the Fasana implementation it actually builds up the full public game tree beforehand. And so the public game tree is like, instead of your individual hand, it's just like the actions as if you were watching two people play poker and you didn't know either of their hands. So like one node could be like the node for like bet, raise, call, and then whatever turn card comes, that would be the single node, and then within that node you have your full range. And so I think this is a pretty intuitive way to do it, and it also makes it so that it's just more efficient, because basically when it's written this way, in each node you have your full range, so it's basically like it contains many information sets within it, and that way it can be efficient, because when you're updating the regrets and the expected values and stuff like that, you just iterate through the whole thing and you just do the same operations over and over again to update the cumulative regret. You're just adding to it or whatever. And so there's some opportunities for performance gains when you just do it that way, compared to making like a giant recursive tree that only kind of makes it to the leaf nodes here and there. It's not going to cover that much of the tree. And when you write it this way, it's kind of like, once you pay the cost of like creating a new call stack by making a recursive call, or it's actually even more costly with the Fasana code base, because he's making a task and putting it onto the thread pool. So once you're in that context and you have everything loaded, like you might as well just go through some other hands and update their strategies and regrets also, because you're already there. And I think that really just has to be the right way to do it. And the fact that he wrote this thing years ago and it seems to have pretty good performance, so I think that's the right track. Although it was kind of disappointing, because I did do all that work trying to figure out how to make the stochastically weighted implementation work, and I thought that there would be some benefits from that, but in the end I think it's just not worth it. So I've basically decided to just scrap that, and what I'm going to do instead is I'm just going to sample for the chance nodes only, and hopefully that'll still work. I think one of the good things of having the solver in the most simple version now is that I can make changes to it and then just compare if it's still finding the right values, so I can just solve like a turn spot with chance sampling on and then without chance sampling on, and if the outputs are different, then obviously I mess up the implementation. And I think that's really the only sensible way to go about this project, because otherwise it's like you're just stabbing in the dark and hoping the thing's going to work, and that's really kind of upsetting and kind of weighs you down and makes it so you don't want to work on it, which is basically what happened to me. And I think there was just one more thing I wanted to go over, because there are some more complicated tasks on the horizon if I want to keep working on this, specifically with the way abstraction works and how I'm going to implement the abstraction within the framework of using this type of solver. And so for the abstraction, I actually realized something only when working on this, from basically from looking at the way Fasana does it with the with the public nodes, the public tree. When I looked at this, I realized that because you actually build the tree before you do anything related to actual the actual cards coming down, is you actually need a separate abstraction for the public tree, and then another abstraction within the individual nodes that then map your individual hands to a bucket. And so I think I actually made an example for how to think about this, or what I'm thinking about. And so like basically like in the full implementation, each of these flops would have their own node. But that's just going to be way too big if we want to solve this thing from a pre-flop on. And so we're going to have to do something like map all these flops to just a single node. And so the way it works normally is if we have the full game solved, within each individual node we'd have like the cumulative regret and strategy for each individual combo. So in reality these would be just numbers, not little tags of strings, but I'm just showing which hand corresponds to the or which combo corresponds to the index in these big arrays that are just going to hold the regrets and the strategies. And that's, if you remember from the previous videos, you basically look at your average strategy over time, and that's what you should be playing from the individual nodes. That's going to be the Nash equilibrium. And so I'm not sure how fine-grained we can get with the abstraction yet. I think it depends on how much I'm willing to pay to have like go in the cloud and make some like use some supercomputer with like a large, a lot of RAM. But like just for this example, like imagine all these individual flops map to a bucket that I'd call ABL, so that'd be like an ace and then a Broadway and then a low card. So like maybe also like ace, king, jack 2 would also go in this bucket. Maybe not, depends on how fine-grained we'd have to get. But then you'd see within that, we then would have to look at the actual hand that's playing out. So the whole time you're solving this thing, you actually are also implementing an actual hand of poker, and you're just mapping it to the abstraction. And so we have the full range of actual hands, and then say we would then have to map each individual combo to a bucket. So here we have like ace king mapping to top pair top kicker, maybe ace jack to top pair good kicker, pocket sixes to a set, and whatever. And then when we go to update the regrets, we actually only have a value for each bucket instead of each individual combo. So in a sense, it's almost like we're sampling, or like we're doing multiple instances of we solved, basically we walked from the node to the end of the value to bubble up the utility. And so we have multiple values for each of these, and then we have to update the cumulative regrets and strategies. And so there's a bunch of things that were kind of confusing me that I wasn't sure if I was actually getting correct, because like I was thinking like, what if we have like 10 combos that are top pair top kicker but only like one bottom set or like two bottom sets, and like does it matter that we're like, do we have to average those together and then update it once, or is there a way to do it so that everything balances out? Because it just seems like there's a risk that if I do it incorrectly, that it'll kind of weight something in one way or another, and it wouldn't be so obvious that anything was wrong. It would just be giving wrong values, which is basically a nightmare scenario for this kind of thing, where you implement the whole thing and then you run it and it doesn't work, and then you just want to jump out the window because you don't even know where you went wrong. And so this kind of thing was weighing me down. And I also realized that there's even more serious problems than just having different numbers of values for each buckets, because sometimes you can get values that are actually undefined. So like here, imagine that we have 6-6 in our range, but we don't have 5-5 in our range. That means that within the public node for the ABL, Ace Broadway Low, sometimes when we're at that node, it's because the actual flop is Ace 10-6, and sometimes it's because the actual flop is Ace 10-5. And so sometimes we have bottom set and we have to update the regret with that value, but sometimes if we're on the Ace 10-5, then the value for that bottom set, it's actually undefined. And so like if you kind of use the value 0 by accident when you're updating the cumulative regrets, you're going to be like penalizing this bottom set hand, even though in reality you don't actually have it. And there's actually like a bunch of things like this that are really subtle, and like I think I figured out how to solve them, but I actually am not sure because I haven't even done it yet. I kind of just like brain dumped and wrote down everything I was thinking of and then stopped working on it. But like it seems like it shouldn't be that hard, but one of the extra complications on this is the fact that the Fasana codebase uses discounted counterfactual regret minimization, which is it's like a slight modification. The idea is that when you first initialize the when you're doing CFR, it's what converges to the Nash equilibrium is actually the average strategy over the entire time that you ran that algorithm. But obviously those first couple iterations are going to be worse than, there's no data there, so like they can't possibly be good, but they're still getting averaged in the entire time you're doing it. And so they figured out how to make it so that basically in the update formula, when you're figuring out the regret and strategy, you basically discount it. That's why it's called discounted counterfactual regret minimization. You discount the earliest values. But again, that was kind of confusing me because within any individual node when we're solving it, it's like it's not a single update where we have only a single regret for each value and a single average strategy, because this thing where you kind of have multiple samples of an individual bucket. And so yeah, it's definitely complicated, and I don't really know if I'm going to be able to solve that, but that is something that I'm thinking about, and I think I figured it out. I'm just not sure. I think once I actually test it, and the good thing is that I'll be able to make an abstraction that I can even like just kind of not even use any complicated data science type stuff, any complicated bucketing strategy. I could actually just do it manually and just pick out hands that look the same for the mapping, and then just see if run it with the abstraction and without, and see if the values are making sense. So that's probably the next thing I'm going to do. And looking on even after that, there's more stuff that needs to be worked on, because the depth limited part of this is still completely scary to me because I don't understand it. There was actually a day, it was like a couple months ago, my power went out, and so I just laid in bed, and I actually had one of the poker papers on my phone, and I just read through the paper that goes over depth limited solving, and it's kind of like boggles my mind how little they actually wrote in regards of like how to actually solve the thing. Like it's crazy. Like counterfactual regret minimization like is not that hard, but like there's just so many papers. There's like literally like some kind of undergrad course from like Gettysburg University or whatever, and then like this depth limited solving, which is like the most important part of solving incomplete information games. It's like this one paper, and he doesn't really explain anything. It's written in like a tiny paragraph. Yeah, and so yeah, I'm definitely going to have to do a lot of experimentation with that. And one thing he did that drives me crazy is in all the examples, he talks about how you have to solve the best response strategy for the opponent from the once you solve to the depth limit. From that point on, you have to find the best response. But in all his examples, he uses the subgame. He's starting at the root of the tree instead of like a node in the middle of the tree. And it seems like it's a completely different case, because the opponent can always navigate to that node with a different range than what you start with. That's kind of like the difference between unsafe subgame solving and safe subgame solving, if you've watched any of the other videos on how people go about that. And so it doesn't, within the paper, he kind of points you in the direction of some of these other papers. There's like a notion of a gift, where like if the opponent is going to take hands to that specific node where it's actually negative, where they're actually losing by doing that, you basically carry the difference that they gave up to reach that node, and then you can subtract that off from the leaf nodes basically when you actually solve it. So like it's kind of like if someone checks all the way to the river with pocket aces and then they win, like say they gave up like $8 in EV by doing that, then when you solve from that point on in the counterfactual regret minimization, like whatever the actual value is, you just like subtract 8 from it, because it's kind of like you already gave them, they already gave the 8 up by even making it to that node. But the thing is, and that makes sense to me, but what doesn't make sense to me is how to solve a best response strategy where the range for the strategy that you're solving it for is kind of like, it can kind of like move, like you can add in different hands and you can subtract different hands, and it doesn't make any sense. And I think I'm maybe just overthinking it, and maybe it'll make sense once I dive in and actually start working on it, but it is kind of concerning. But one thing that I think is a good thing is that that's only one of the ways in the paper that he talks about doing it. With depth limited solving, you can either solve the best response in the rest of the tree after you solve to the depth limit, or you can just make, or you can do like a basket of different kind of pre-organized strategies. So you can like make it so that, say you solve to the depth limit, and then there's like one opponent that like plays really passive all the way to the river. There's one opponent that plays passive on the turn but then aggressive on the river. There's one calling station, there's one maniac, you know, and like the idea is that whatever the depth limited solution comes to, it also has to be robust against all those different strategies. And there's a paper, it's written by some Chinese professors who used that approach and apparently had really good success. And so I think in the worst case, if I can't figure out this the best response ideas, I can do that other thing, although it's a little bit less exciting to me, I think, because I think the best response thing kind of seems algorithmically interesting, whereas the other thing just seems like a lot of work, like tedious work, and like, I don't know, maybe if it actually works it'd be worth doing, but I'm kind of rambling now. So yeah, thanks for watching this video. I do want to keep working on this. It's just hard because it's just going to be so much work and like it's really not worth it for me, I don't think. But in terms of money, I'm just doing it because it's kind of fun to work on. And so if you like this video, please like and subscribe, and thanks for watching.